All right, so welcome to the Real-Time Digital Signal Processing Lab at the University of Texas at Austin. So this is lecture 7 on interpolation and pulse shaping. So one of the takeaways for today's lecture is that oversampling is a good thing. That came up in midterm 1 in the last question. But there's a trade-off, right? The more oversampling we do, the more complexity we have to have in our system. We have to process the samples faster, need a faster processor. Filter orders go up typically as we increase the oversampling rate to meet the same magnitude specs, and now we need more buffering, and we also now have more multiply accumulates per sample and more samples per second. So there's a trade-off point where you say enough oversampling, maybe it's 4x, 10x, 500x, depends on the application. Also, another takeaway today is that we're going to do a lot of interpolation and pulse shaping, and we'll use this in the transmitter and receiver designs for the rest of the semester. Pretty useful stuff. We'll start using it next week in lab. All right, so this will be take up most of 2 lecture periods. So we'll go back and revisit discrete to continuous time conversion. This was, we'll see it, it's part of digital to analog conversion. We'll look at interpolation, several pulse shapes, rectangular, triangular, sinc, and raised cosine. And in lab, we're going to be using the raised cosine quite a bit in the communication system in both the transmitter and receiver that we'll implement. And we'll do a demo, of course. We've done this demo before. We'll do it again. This was sampling and interpolation. All right, so this slide we've seen before, so you can revisit this. All right, so for data conversion, we have 2 different sides of the story. This is one of many places that interpolation comes into play. It's not the only. So again, we talked in lecture 4 about sampling. So with sampling, we have a nice sampling theorem. It tells us that we want to sample at, there's 2 sides of that sampling theorem. One, it says that our sampling rate should be greater than 2f max. It also tells us, again, that f max, that is to say the maximum frequency we can represent, is less than 1/2 the sampling rate. So if I pick a sampling rate, it tells me the maximum frequency that I can represent is half the sampling rate. Which kind of makes sense. Because if I sample a cosine at that frequency, I can capture it. If my cosine's at a higher frequency, it's going to alias. We also know to convert from, so we know to convert from continuous time to discrete time frequencies. So I know that if f naught is half the sampling rate, then omega naught is pi. So if f naught so the highest frequency that we can represent in discrete time is pi radians per sample. If f naught were minus half fs, then omega naught is minus pi. So this gives us the extreme points in discrete time for frequencies, right? Everything else is going to be obtained. Any other discrete time frequency is obtained by periodic extension. So our fundamental period in discrete time frequency domain is minus pi to pi. We could also go 0 to 2 pi if we like. Any 2 pi interval will be fine. We tend to go minus pi to pi for filters, but for Fourier analysis, we often go 0 to 2 pi. Go ahead, depends. Yeah, either side. Remember, if our signal is real valued that we're going to sample, then it's going to have both positive and negative frequencies, and there'll be symmetry. Yeah, so you do that. So if I'm going to have a cosine at, so if I sample a cosine that's has a frequency f naught, then I'm going to see both a positive component at f naught and a negative component at minus f naught. So the Fourier transform of the cosine is a pair of direct deltas. Right. So back in the Fourier domain, if I have room to draw it here. All right, so take the Fourier transform of the cosine. This is a two-sided cosine, so I get a direct delta at f naught and a direct delta at minus f naught. So I'm going to have both positive and negative frequencies present if my signal is real valued in the time domain. And you can kind of see that if I replace f naught with minus f naught, it doesn't change the cosine. Still cosine 2 pi f naught t. All right, so as we talked before, we have frequency content really at all frequencies because of at least thermal noise, the random motion of electrons due to temperature. So no matter what sampling rate we choose, we're going to have aliasing. And so it's up to the design of this analog low-pass filter prior to sampling that will help us control the amount of aliasing that happens. Right? So we choose a stop band attenuation to reduce dramatically frequencies at or above half the sampling rate so that when they alias, we don't see them if it's an image processing application, or we don't hear the aliases if it's an audio application. Okay. The quantizer also is at play in this case. We'll talk more about that in Lecture 8. The number of bits that, per sample that come out of here actually will let us set the stop band attenuation. And that stop band attenuation is basically 60 dB per bit that we want to support in the quantization plus a small offset. So it tells us what the stop band attenuation needs to be. All right, so that's the A to D side. On the D to A side, which is more what we're going to talk about today in Lecture 7, in the digital to analog conversion side, we have a discrete time and digital signal that we'd like to approximate as a continuous time analog signal. We'll do this in 2 steps. Again, in iPrice, this is I'll put a hat over the X here to say it's an approximation of what we might have started with on the other side. So if I start with X of t here, prior to running through A to D conversion, what will come out is X of n. If I want to then try to go back to continuous time analog domain. Hey, Scott, we're getting some feedback from the speakers, or probably from the other room. Thanks. All right, so here we're going to try to reconstruct, and the sampling theorem tells us it's at least possible. It tells us that we can reconstruct frequencies up to half the sampling rate. Right? Remember, the sampling theorem assumed that there was no frequency content above f max, which is an idealism and not going to hold in practice. But what we can take out of the sampling theorem as far as practice is concerned is that when we do this reconstruction, when we do digital analog conversion, we have the hope that we can reconstruct frequencies from 0 to half the sampling rate. Any frequencies that this digital analog conversion generates that's greater than half the sampling rate, what are those frequencies? Are they here in this discrete time signal? No. They're artificially introduced by the way that we go about converting from discrete time to continuous time. We got artifacts in that conversion process. We'll talk about that today. That then leaves a designer the freedom to design this analog low-pass filter to try to remove or clean up those artifacts. So the more you're willing to put into the analog low-pass filter, the less work you have to do in the discrete time to continuous time conversion step, or vice versa. If I don't want to do much work in the discrete time to continuous time conversion step, I have to do more work in the analog low-pass filter. And this is more generally the case. We can, the more we're willing to do on the discrete time side, the less we have to do on the analog side, the continuous time side. Go ahead.
When you talk about like artifacts and stuff, where you talk, for example, like like sample and hold, where it's very jagged and those jagged edges can be seen in high frequencies.
Correct. So any interpolation that we do here, which is this will be interpolation, this conversion from discrete time to continuous time, basically have to connect the sample values that I know so that I have a signal that occupies all time for continuous time. That step will add harmonics and those harmonics will eventually exceed half the sampling rate. So we'd like to remove, by means of analog low-pass filtering, any of these harmonics that will stretch out. So if this were a cosine and I do conversion, I'll get harmonics of that cosine frequency. I'll also get harmonics of the sampling rate. So harmonics of the sampling rate are going to exceed half the sampling rate very fast. Right? So this filter is basically to clean up both sets of harmonics that happen. And a lot more to come in lecture 10 on data conversion next. I guess that's toward the end of the semester. Okay. Now these two analog low-pass filters have very similar design considerations, and you could really reuse. So again, it depends on how much work you put in here. So if you don't do much work on this discrete to continuous time conversion block, then you can simply reuse this analog low-pass design. If you want to do more work in the discrete time continuous, in fact, if you do enough work in the discrete to continuous time conversion step, you may not even need the analog low-pass filter, or it won't help you, or you need a very simple biquad or something. You don't need something too involved. Okay, so let's talk about this in a little more detail. So for this discrete time to continuous time conversion block, the input will be a sequence of samples called y of n, and the output's going to be a smooth continuous time function obtained through interpolation by connecting the dots. So let's go back to where y of n comes from to begin with, or where it could have come from. So it could have come from a continuous time signal, y of t. And y of t, in this case, will be a cosine of fixed frequency f naught and a constant phase phi. Now, if I sample this without aliasing, what I want to make sure is, so I start with y of t, which is an ideal two-sided continuous time signal, band limited, and I sample this. I want to sample at remember, it's ideal here, so just greater than 2f naught is fine. I don't have any bandwidth. This is a two-sided signal, so I have zero bandwidth, but I have two frequencies in the cosine, as I showed on the earlier slide. I have a frequency content at f naught and at minus f naught. And as long as my sampling rate is greater than 2 times f naught, I'll be fine. I satisfy the sampling theorem because my f max here is f naught. Okay, so if I do that, then I get very familiar, we've done this before, we'll get y of n we can write this a couple different ways. The way we've been writing it, which I will do again, is that we do it in terms of, we replace, so y of n is going to be, this is going to be y of t, where we replace little t by these snapshots at integer multiples of the sampling time, or we can do it as integer multiples of 1 over the sampling rate, which is what we've been doing. And we get, right now, a fairly familiar form right, which is 2 pi times f naught divided by fs. And this, again, this frequency here is a discrete time frequency after sampling. That's omega naught in radians per sample. We've needed that all as far back as lab 2 with sinusoidal generation. And even lecture 1, so all the way back to really the first full week of lecture. Okay, so that's what we would, again, this is all a nice idealism from sampling, assuming two-sided signal and all that, so nice idealism. So another way to write that is this, so where we replace Fs by 1 over Ts. So this is another way to write it. It's the same, that's the same structure, same thing. All right, so we've just taken Fs and replaced Fs by 1 over Ts. Oh, I forgot the phi. And again, as long as the phi is constant, it's not going to affect us much at all. Really, it's just an offset. Doesn't affect the frequency content of the signal. Okay. Now, what we'd like to do is, if this is our sampled signal, discrete time, and here I don't have quantization, but in principle it could be quantized. The amplitude could be quantized. We'd like to have this converted to the original cosine, if we could. Now, in this case, we have a chance to do that because we started out with an ideal signal. That's two-sided, which is an ideal two-sided signal. So in theory, we can hopefully get back to that if we don't have any aliasing. So we'd love to come up with a way to go from discrete time to continuous time so that we get back to where I started. And now this depends on the way that we do the interpolation. Okay, so again, we start with little y of n, which I show here by a stem plot with, some people call it a lollipop plot. I'm okay with that. I don't think there's a lollipop command in MATLAB. It's stem, right, in MATLAB. Okay. So I have my discrete time signal shown as a stem plot. Now I've got to come up with a way to connect the dots so that I have a continuous time signal. And there are lots of ways I can connect the dots. We've talked about some ways to do this, right? We could draw straight lines between the dots. This is what plotting routines tend to do by default in MATLAB, for example. Fine, and you can be more sophisticated. Plotting routines have other options on how it does interpolation for plotting. I've just hand sketched an interpolation here. I could use zero order hold. What would happen if I do zero order hold? How would you describe it? Staircase, right? So I could hold this sample until the next sample comes, hold that sample till the next sample comes, and I get a staircase approximation in the reconstruction. Now that's got a lot of harmonics. But the good news is I'm going to follow this conversion step with an analog low-pass filter. It's going to remove all the harmonics and all other frequencies, or at least reduce their strength for any frequencies above half the sampling rate. So this will remove a lot of these harmonics and round out the edges for me. Go ahead.
How do you know that you want to do that, though? Because it could be that your original signal was, in fact, the staircase.
Well, the thing is, if the original signal in continuous time were a staircase function, it would have incredible harmonics at the very high frequencies. So if I sampled at only just above twice the fundamental frequency of that, which is 1 over the fundamental period, I would filter out all those harmonics and I'd get back a sine wave. So it's another trick. There's a trick there in how you can convert a square wave into a sine wave. But you'll pick up the original square wave and all the harmonics up to half the sampling rate. And any harmonics above half the sampling rate will get attenuated by the analog low-pass filter before sampling. Yeah. So it'll be more than a cosine. You'll get the fundamental frequency and a certain number of harmonics. Okay, so lots of ways I can do this. Now I can really fit I can use other functions in here. So we'll use a sinc function in just a few minutes to do this, or a pulse. So any pulse shape I can use. So in the zero order hold or sample and hold, I only need to know one sample value, and I just hold it. For linear interpolation, how many samples do I need? 2. So I need to keep 2 in memory, the current one and the previous one, and I can just connect that with a line. Right, so now I connect it with straight lines as best I can draw them. And again, if I'm oversampled, if I've really got a lot of oversampling, then when I connect by straight lines, it's going to look pretty good. So when you plot in MATLAB by default, and you use 1,000 samples for your horizontal axis, it's going to look pretty good. You're not going to see these lines, but you use 3 or 4 or 5 or 10 samples over the horizontal axis, and you'll see these lines connecting the dots. Okay, what we'd like to do is come up with a way, though, is to get back to our original cosine if we can. And the way that we can do that ideally, we'll see shortly, is to use a sinc pulse that ideally, again, this is going to be idealism, is two-sided. So we can't build that. But if we could take this sample and overlay a sinc and we took this sample and we multiplied it by a sinc centered here at 1, and this sample at 2 and put another sinc and centered by 1, and we added up all the results, we'd get back exactly the cosine. The sinc is the best thing to do. What's that? It's ideal. We can pretend to do anything we want in ideal, right? We have an ideal two-sided signal. I have a two-sided, interpolation pulse. I mean, these are all ideal. We can't build any of this stuff. But ideally, yes, we can do that, which is kind of nice. We also here don't have any quantization in this slide. We assume exact representation of analog amplitude values. Lots of idealisms here. But at least it tells us it's possible. At least there's an ideal world where all this works just nicely. Okay, so again, this has to be a two-sided sinc. Okay, and a couple things you'll notice is the sinc that we would need is a sinc pulse in the time domain. What's the Fourier transform of that? It's rectangular pulse, or a rectangular shape. It's an ideal low-pass filter. Okay, so think back to when we talked about sampling. If I'm going to sample a signal, and I obey the sampling theorem, again, this is all idealisms, then how do I reconstruct? I apply a low-pass filter. Okay, so the ideal low-pass filter is this rectangular pulse. Or the ideal low-pass filter looks, here's the ideal low-pass filter. It's a nice rectangular pulse. The impulse response for this filter would be a two-sided sinc. Can't build this in practice, but it's nice to know that it exists in the ideal world somewhere. So the sinc is kind of the nice shape we'd like to do. So what can we do in practice? I can't do a two-sided sinc, but I can do I can't even do a one-sided sinc. That's crazy. It's a lot of memory. I'd like to make an FIR filter out of this, a windowed sinc. So I can take the sinc and truncate it to say, four intervals of time, 4 sampling periods, or 8. So in lab, you'll do 4, 6, and 8. And the demo will use this 4 that I'll do later. And it turns out it's pretty good, even after being truncated. Okay. Now, if we don't obey the sampling theorem, so any frequencies that are at or above half the sampling rate, when we sample, we'll alias to frequencies between minus half the sampling rate and half the sampling rate. Also, if we so we won't get, if we have aliasing to begin with, this will be different. Right? This is without aliasing. All right, so let's talk about the general form of discrete time to continuous time conversion, and it should look familiar. What's your guess? What kind of operation is this? Yeah, it's an impulse. It's a pulse train. convolution, so underlying all of this is a basic signal processing operation. There was sampling in here. Convolution, so what kind of system is described by convolution in the time domain? FIR, it's a filter. In this class, you're in good shape, right? Half the answers are filters. Yeah, so this is a filtering operation in the end. Okay, so here's a general, this is a linear systems viewpoint of interpolation. There are other viewpoints. So the general form of interpolation is the sum of weighted pulses. So if I pull this apart, I have a sequence, y of n. I want to convert this from discrete time to continuous time. I connect the dots by picking a pulse function, p of t. Lots of choices for that in this context. And then I'm going to do what? I'm going to take my pulse shape and I'm going to flip and slide the pulse shape about the sequence values that I know. What's a little bit unusual is that the outer variable of this convolution is continuous time. The placeholder variable in the summation is discrete time. Okay, so this is the placeholder variable. Placeholder variable of the summation is discrete time. And the outer variable is in continuous time. And this is a way to convert from discrete time to continuous time. How visible is the purple back row? Not there. It's okay. We'll make it good. All right, so the outer variable is in continuous time, and the inner variable is in discrete time. So it's a mixed signal convolution. I'm mixing continuous time and discrete time. The input is discrete time, the output is continuous time. So I can pick any, and we'll go through several pulse shapes here this lecture. We'll go through rectangular, triangular, and sinc, and we should also get to raised cosine. Now, these pulses, depends on the choice, you may or may not have an overlap here because the interpretation between adjacent discrete time samples, what's the width in continuous time? It's a sampling time. Okay, so we have to associate a continuous time quantity with these discrete time samples. So the sampling time tells us what that is. Now, the pulse shape could be longer than a sampling time. So for rectangular pulse, the duration is just the sampling time. This would be the sample and hold. The triangular pulse, what do you think that duration is? How many samples do I have to keep in memory? The triangular pulse is the linear interpolation case. Drawing lines. 2. So I have to keep track of the current sample and the previous sample, and I connect the dots. So its width is 2TS. So TS for rectangular, 2 times TS for triangular. And I'll have more slides on this to follow. So you may get overlap in the time domain, and you will for any pulse shapes other than rectangular on this list. There'll be some overlap. No, that's fine. It's not a problem. And then also in the frequency domain, we'll see if there's overlap or not. One would expect some. I would. The pulse shapes we're using are going to have unit amplitude or unit area. And again, as I pointed out in the last comment, the above formula is related to discrete time convolution. Again, it's really mixed signal. This is really a mixed signal convolution. This is really a mixed signal operation, or mixed signal convolution. Now, these pulse shapes are finite in extent, so they can be represented. So I can actually do the interpolation completely in discrete time. So I can actually do the interpolation step in discrete time through upsampling. And then I can go through a very simple discrete time to continuous time converter using zero order hold. So I can actually do quite a bit of this work completely in discrete time, do a very simple conversion through rectangular pulse shaping or equivalently sample and hold, and then follow that with a really good analog filter. So a lot of things, lots of ways I can do this. I can divide the processing into the discrete time side and the continuous time side, many ways to do that. All right, so let's talk about interpolation more generally and look at two linear system approaches and one that's two linear systems that are data independent, and then an approach that would be data dependent. So it's a pretty common situation. You're reading an article or you've got a set of data and they don't give you every point you need. So you try to eyeball a point that you want that's not on the table. So interpolation from tables is, again, here's an example table, very simple table for 4 entries, have an x and an f of x. This also might happen with mathematical tables and handbooks. Those are less common these days, but again, I think reading something online is more likely the case. Or I have a graph where I can read off some values and I'm trying to interpolate between values that I know. Anyway, so using mathematical tables of numerical values of functions to compute a value of the function is interpolation. So here's an example. I want to estimate the function of 1.5 from the table. Lots of ways I can do it. The zero order hold case, which is the sample and hold case, is we'll just simply take the value to be 1. Okay, the way to see that graphically or visually is, again, I have x on the horizontal axis, f of x on the vertical axis. I have the points that I know from the table, again, shown as a stem plot. And then I have 2 different linear system ways to connect the dots. One is hold, sample and hold. That's in, I'm going to go with blue. Is that blue? We good? Good. And then connect the dots with a line, linear interpolation. I have that as red dashes. So if I want to know f of 1.5, and I want to look at the zero order hold case, it would just be 1. If I want to use linear interpolation, it'd be the average of the 2 closest values. So that would be 2.5. All right, so the 2 closest values are f of 1 and f of 2 is 4. So f of 1.5, which is the midpoint, would give me an approximate value of 2.5. Now this, you can kind of eyeball the trend here. This is really f of x is equal to x squared. So this is really just simply, so I could then, another way to go about the interpolation is to find the formula that connects x and f of x. Not always easy to do. In this case, I made this data up so it fits nicely. So what we can do is do curve fitting, which is to take a polynomial and try to fit the data. I have 4 points here, so I could do 4 unknown coefficients. So I can do third order polynomial, a0 plus a1x plus a2x squared plus a3x cubed. And I get 4 equations and 4 unknowns. Right? So I know when x is 0, I get 0. So that tells me that A naught is 0. I put in x of 1. The answer is 1. So it's three unknowns in one equation. But all totaled, I get 4 equations and 4 unknowns that I can solve for the answers. And what I'll get is A naught is 0, A1 is 0, A3 is 0, and A1 is 1 after doing the back solving. So now that I have a formula, which is now data dependent, I can now interpolate anywhere I want along x. Any value I want, right? It's just a formula. So now f of 1.5, I just compute the formula and I get 2.25. Okay. Now this last one is a cubic spline. This is the way that interpolation is done commonly in image processing. This is the technique, and it's extremely good. Visual quality is extremely high. Using either of these in images, what do you expect to happen? What visual artifact do you expect to see? Okay, you're on the right track. Certainly these are not great filters. All right, we'll see their frequency responses soon, but they are filters. And what do you think their frequency selectivity is? Remember, in the end, this is a filtering operation. The flip and slide convolution from the previous slide, mixed signal. What's the frequency selectivity you think of a rectangular pulse? Low pass. And triangular pulse? Low pass. So what do you think the image is going to look like after you go through this filter that's low pass? It's going to be blurred. So you get these using either zero-order hold or linear interpolation on image for image interpolation gets a blurred image. Go ahead.
Aren't like sharper edges correspond to more like high pass?
Yeah, you get high frequency. So there are some high frequency that get through, but it's 13.5 dB down from pass band. So they do get de-emphasized or attenuated. They get through, but not at anywhere near the strength that the low frequencies get through.
So the low pass effect is dominant.
That's correct. That's correct. So if I want to say take an image and make it 4 times bigger in the horizontal direction and 4 times bigger in the vertical direction, then I'll connect all those basically 0 pixels in between the points I know through curve fitting. And it looks extremely good. Really. Not blurred. Really nice stuff. So cubic splines are the way that do it in imaging, typically. All right. Let's go through a few of these pulse shapes. So rectangular pulse for our pulse shape, this is a zero-order hold case or sample and hold. Easy to implement in hardware or software because all I need to do is hold one value until the next value comes in discrete time, hold, sample, and hold. It's very simple, right, to implement. Mathematically, it means that the pulse shape is a rectangular pulse, and the duration of that rectangular pulse is one sampling a period. Now here I show you a non-causal version. In practice, we would probably use a causal version. It depends on the application. If we've buffered all the data, it doesn't matter. But if the data is streaming at us, we would tend to use a causal version of this. So the causal version just starts at 0. All right, there's your causal version. Fourier transform is the same except what? What's the difference? The shift in time, which means in the Fourier domain, we have a change in magnitude, change in phase. That's it. Doesn't change the magnitude. All right, so the Fourier transform, again, this would be the rect pulse command in MATLAB if we wanted to generate a discrete time, at least a discretized version, I suppose. All right, the Fourier transform, just the sinc. What's the null bandwidth? It's fired by midterm 1. What's the null bandwidth? For the sinc. 1 over TS. It's 1 over the width or length of the rectangular pulse. Good. Another way to think about it, the longer I can observe something in time, the more accuracy I have in frequency. Right, so the longer the pulse shape, the null bandwidth gets smaller, 1 over TS. If TS gets bigger, 1 over TS gets smaller. This is a fundamental trade-off between time and frequency. All right, now in the time domain, there'll be no overlap between P of T and the adjacent pulses because the rectangular pulse is only as wide as the sampling time. Another way to, why that's important, I only have to know one value. I know one value of y of n, and I hold it. I don't need to know any other values. Frequency domain, I'm going to get complete overlap in the frequency domain, and it's more interesting than that because the sinc in the, right, this is our Fourier transform as a sinc. It's two-sided, has all frequencies in it. Not very practical. The spectrum is not band limited. So what do we do? How do we fix this? And this is our discrete time to continuous time conversion block. So what comes next? Analog low-pass filter to clean up, get rid of all these frequencies that are above half the sampling rate. And we've got a lot of them, right? We have a sinc here that just keeps going out to infinity and minus infinity, decaying slowly with frequency, 1 over f. Right, so here's the decay rate. Very slow decay rate. Its frequency goes to infinity. All right, Sinc function, just a review. We've used it already quite a bit, but it's nice to throw this one up in the talk. So the Sinc X is, again, the different books do it differently. I tend to do, I guess I've learned both, depends on the book. So here's Sinc X is sine x over x. The other possibility is what sine pi x over pi x. But the shape won't change. Right, it would be a scaling of the horizontal axis in the other case, but the shape doesn't change. All right, so then the question, just to make sure you maybe recall this from signals and systems, how do we compute the sinc of 0? We got numerator and denominator going to 0. How do we do that? I heard it. L'Hopital's rule, right? So L'Hopital's rule, been somewhere, maybe high school, maybe here, first year, who knows? So what does L'Hopital's rule tell us? What do we do? Take derivatives of numerator and denominator separately, and then take the limit. So we're good. So we take the derivative of x with respect to x, 1. That's good. And we take the derivative of sine, cosine. So the derivative, so we do L'Hopital's rule, then it becomes a limit equals 1. Right? It's good. Now, the sinc function is even symmetric about the origin. We've got 0 crossings at regular intervals except at the origin. And so for this definition of the sinc, the 0 crossings are at plus or minus pi, plus or minus 2 pi. The other version of sinc, where are the 0 crossings? The other version is, how about we do other? I don't know. Call it other. The other version. Right? That's the MATLAB version. What is that one? It doesn't affect, the sign of 0 is still 1, and the 0 crossings are now going to occur at what values? Yeah, plus or minus 1, plus or minus 2. Good. Amplitude in both cases will still decrease proportional to 1 over x. So it's a very slow decay as x goes to infinity or as x goes to minus infinity. Just takes its time. The amplitude takes its time going to 0. All right, triangular pulse. This is linear interpolation. Again, relatively easy to implement in hardware or software, very common in audio. They use linear interpolation between, or anytime you have conversion between sampling rates that are very close in value, say 44.1 kilohertz and 48 kilohertz, just do linear interpolation. Take a block of 48,000 samples and linear interpolate them to 44.1 kilohertz playback. Pretty easy to do. So relatively easy to implement in hardware or software because I just need two data values at any one time and just draw a line between them. So it's not as easy as zero order hold. I need 2 points instead of one, but it's a pretty simple filtering operation. So here's a triangular pulse in the time domain, unit amplitude. The width is now doubled over the rectangular pulse. Got to make sense. I need two samples to produce an output value, to produce output. So I'm going to get some overlap. So if we look at the adjacent pulses, they're going to look like this. Right, so they're going to overlap in time domain. Right, so this is the pulse at sample 0. This is the pulse at sample 1. This is the pulse at sample -1. This will always happen because you need, the triangular pulse is always going to look at two samples at one time. So in other words, if you look at any, remember, what was the formula? The formula was flip and slide. So basically, for every sample, I'm going to flip and slide a triangular pulse in continuous time about each sample. So if I have 1, 1, 1 as my sample values, what I've drawn here, then the value at any point between 0 and TS is simply the sum of these two triangular pulses, which is just going to be 1, which makes sense. So if I have 1, 1, 1, the interpolation will just be all 1, right? But I have contributions for any particular value in time. I have contributions from the samples, the two nearest samples to me when I use this type of interpolation, triangular pulse. So I have two ways to think about it. Either I take a sum of all these individual pulse shapes because of flip and slide convolution, or alternately, I can think about drawing a straight line between the points that I know. Get the same answer either way. But this way gives us a linear systems view of what's going on. Fourier transform is the Sinc squared for this one. And the way you can compute this, well, the triangular pulse can be determined or computed by a convolution of the rectangular pulse in the previous, I guess, 2 slides ago with itself. And we have to scale things to get the amplitude back to 1. No problem. And so if we convolve two rectangular pulses, each is of width capital TS, the convolution means the width is 2 times TS. It's wider. And so if I convolve in the time domain, it means I multiply in the Fourier domain. So all I need to do is multiply the the Fourier transform of the rectangular pulse with itself, and then scale by, or multiply by 1 over TS. That gives us this Fourier transform. So the good news is it dies out more quickly in the Fourier domain. Dies out at 1 over f squared. That's good news. It's a better low-pass filter, in other words. Bad news is it still has infinite two-sided extent in the Fourier domain, but it's okay. We're going to follow this step, this conversion step with an analog low-pass filter anyway. Okay, probably a good place to stop. So this will be part 1 of lecture 7, and we'll do part 2 next time.